Okay, so today we will be discussing a problem on Venturimeter. Let's see what the problem says. Find the discharge of water that is flowing through a pipe of 30 centimeter dia placed in an inclined position where a Venturimeter is inserted, having a throat dia of 15 centimeter. The difference of pressure between the main and the throat is measured by a liquid of specific gravity 0.6 in an inverted U tube, which gives a reading of 30 centimeter. Okay. Now we have an inclined pipe through which water is flowing and the flow is taking place in this direction. Okay. So the diameter of the pipe is given and in this pipe a Venturimeter is inserted. Okay. So this is the Venturimeter. It has a converging part, it has a throat and a diverging part. And this is the pipe. Okay, the diameter of the pipe is given as 30 centimeter. So the inlet section is marked as 1, whose diameter is going to be 30 centimeter, and the throat section has been marked as 2, section 2, okay, whose diameter is 15 centimeters. So you can calculate the area at section 1 and area at section 2 from the values of this diameter. Then we have a differential manometer, a U-tube manometer, which is also inserted across section 1 and section 2, which will help us in measuring the difference in head, okay, the difference in pressure and the potential head between these two sections, that is 1 and 2. So the specific gravity of the fluid which is inside the manometer is 0.6, and the difference in level between the two levels, or the difference in head between the two levels of this fluid inside the manometer, is also given as 30 centimeter. Now students, what is the specific gravity of the fluid which is flowing through this pipe? The fluid which is flowing through this pipe is nothing but water, which has a specific gravity of 1. So obviously the fluid which is inside the manometer is lighter than the fluid flowing through the pipe. So as we had discussed in the previous videos, that whenever an inclined Venturimeter is there with a U-tube manometer containing a liquid lighter than the liquid flowing through the pipe, we can calculate the difference in pressure and potential head as this formula: x into 1 minus SL by S0, where x is the difference in head of the fluid which is there in the manometer, SL is the specific gravity of the lighter fluid which is inside the manometer, and S0 is the specific gravity of fluid flowing through the pipe. Clear? Now, so with the help of this formula, we can easily calculate the head difference. Okay, so head difference is given by what? The summation of pressure head and potential head at section 1 minus summation of pressure head and potential head at section 2. Now this expression is also equal to this. So now we have the values of x, we have SL, we have S0. So what is x? X is nothing but the difference in level of the liquid inside the manometer, which is 30 centimeter. So what I have done here is that I have first calculated the difference in pressure and potential head at between two sections. So x is 30 centimeter into 1 minus SL is 0.6, the specific gravity of the fluid inside manometer, and 1 is the specific gravity of water. Okay, so H is coming out to be 12 centimeter. Clear? Now let's see the last part of the problem. The loss of head between the main and the throat is 0.2 times the kinetic head of the pipe. Okay, so what is the value of the kinetic head of the pipe? See, we have two sections. We can have two kinetic heads. Okay, we have section 1 and we have section 2. But in this case, since it is mentioned that the head loss is equal to 0.2 times the kinetic head of the pipe, since the word pipe is mentioned, it means that we have to consider the velocity of the flow which is taking place through the diameter of the pipe. So this section or this section is the pipe through which the velocity V1 will be there. Okay, so the kinetic head of the pipe is going to be V1 square by 2G, because this velocity should be corresponding to the velocity of the flow through the pipe and not through the throat, right? So HL, which is the head loss, will be, this is HL, this is equal to how much? This is going to be equal to 0.2 times V1 square divided by 2G. Okay, it is not going to be V2 square, because V2 is the velocity corresponding to the throat of the Venturimeter. So this is not the section of the pipe, this is the section of the pipe. So we have to consider the velocity at section 1, right? Now see, we have the value of head loss as this. We have the difference between the pressure and the potential head between section 1 and 2 as 12 centimeter. Okay. Now let us see what the question asks. The question is asking us to calculate the discharge of water flowing through the pipe, right? So in order to calculate the discharge flowing through the pipe, we will first implement the Bernoulli's equation. Okay. So by now I think everyone is related to this equation of Bernoulli, which is equal to the summation of pressure head, potential head and kinetic head at section 1 is equal to summation of pressure head, potential head and kinetic head at section 2 plus head loss. So the value of head loss is given as how much? 0.2 times the kinetic head. Okay. Now if you take HL, head loss, on the left hand side and all the other expressions on the right hand side, you will be getting this expression. Okay, and in this expression what do we have? See, this part we have already calculated before. Okay, let me show you. See, this part H, which is equal to this, has already been calculated as 12 centimeters. So we will simply substitute the value of H in this equation. So what do? We have the HL as 0.2 times V1 square by 2G, HL as 0.2 times V1 square by 2G, and H is equal to 12 centimeters. So we put the values in this big expression, and if we put those values, we will be finally getting an expression that will look like this. So see, in place of HL, we are substituting it with 0.2 times V1 square by 2G. And this big term is being substituted by the value of H, which is equal to 12 plus V1 square by 2G minus V2 square by 2G. These two expressions will remain the same. Now, if you simplify, you will get another equation or another expression that will contain V1 and V2. Okay, I will ask you to simplify this expression by yourself, right? So our main aim in this problem is to calculate the discharge. Okay. So in order to do so, we have first implemented the Bernoulli's equation, right? To get this expression, which is containing only the term V1 and V2. G is known to everyone. Now, second, what we are going to do is that we will apply the continuity equation. So what does the continuity equation say? It says that the discharge across any section of a fluid flow in a pipe is always constant. So if the discharge along a pipe at any section is constant, then we can say that area into velocity or discharge at section 1 will be equal to discharge at section 2. And what is the formula for discharge? It is nothing but area into velocity. Okay, discharge Q is given as area into velocity. Okay, so at section 1, area into velocity will be equal to the area into velocity of section 2. So from here, if we will derive a term which is equal to, from this expression we will be deriving a relationship between V1 and V2. Clear? Let me just clear this. Okay. So from here we have already calculated the value of A1, which is equal to 706.85, and the value of A2 is how much? It was 176.7. Okay, so with the help of this expression, we will be deriving a relationship between V1 and V2. So see, V1 is equal to the ratio of A2 by A1 into V2. So V1 is equal to, how much was A2? A2 was 176.7 divided by 706.85. This term into V2. Okay, so if you simplify this term, we are getting V1 is equal to V2 by V2 by 4. Okay, so this is the relationship between V1 and V2. Fine. Now in the last part, what we are going to do, see, we are going to plug this value of V1 in this expression so that we have only one unknown here, that is V2. Clear? Let's see. See, I have plugged the value of V1 in this expression, okay, in this V1 here, and then we are having only one expression, that is V2. And if we simplify this equation, we are getting the velocity at section 1 as 157.4. So as we know that the discharge through section 1 will also be equal to the discharge through section 2. So since we have already calculated V2, we can easily calculate the discharge now, which is equal to area at the section 2 into the velocity at the section 2, which is equal to this 27.8 liter per second. In the other way, if you plug the value of V2 in this expression, okay, then we will be having only one unknown, that is V1, and then if you calculate the discharge, which will be equal to area at section 1 into velocity at section 1, the same value of discharge is going to come out. Okay, so this is it. Please do the problem by yourself, and if you have any doubts, any suggestions, you can write down in the comment box.